relevant. And what she's found in repeated experiments, she's done more than 7 of these, consistently, higher levels of CO2 are enhancing the growth rate of both strains. But there's differences when it comes to toxicity. Specifically, she's seeing higher toxin content per cell at high CO2 for the New York strain, but not for the Canadian strain. And they actually have different toxin profiles and congeners, and that may be the reason behind that. But beyond the lab, she's also looking at the field, and that's what's shown here. This is Northport Harbor. This is a system we've worked in for a while now that has repeated Alexandrum blooms. It has an inlet out to Long Island Sound here, and you can see going back towards the harbor, it's the region where she's seeing the highest densities of Alexandrum, 8,000 cells per liter, and getting lower as she's going further out. As again, the pattern we see consistently. We've also been mapping out the levels of CO2 in surface waters using an in situ continuous monitoring probe. And when we're doing that, what we're finding is that the intense parts of the blooms are coincident with high levels of CO2. So that's how things are playing out spatially. On a temporal basis, she's also looked at the progression of bloom. So here's bloom in 2011, initiating in April, going through into May. And concurrently, in addition to looking at the density, she's been measuring CO2 in 2 ways: that continuous monitoring probe, also by taking discrete samples of measuring total inorganic carbon and then measuring pH and calculating the levels of CO2. You can see there's some decent correspondence between the two. But importantly, over the course of the bloom, the levels of CO2 are actually increasing. So again, towards the end, where we're seeing over 1,000 parts per million, 1,000 parts per atmosphere. So what she wanted to finally understand is in an ecosystem condition, given that we know this range of CO2 from, say, 300 to 1,500 parts per million, how does that affect the Alexandrum in a total community, not just within an individual culture experiment? And that's what's shown here. So this is a series of experiments during the same year where she's exposing whole populations to 3 different levels of CO2. And you can see that on a consistent basis within these experiments, just like in the lab experiments, within an ecosystem setting, higher levels of CO2 are resulting in higher densities of Alexandrum. And this finding is not alone. In fact, we're a little late to the game on the Alexandrum front. This is now the 4th species of Alexandrum that's been shown to grow either faster or be more toxic under higher levels of CO2. You can see there's other species out there. There's the Pseudonychia that I mentioned before, becoming more toxic at higher levels of CO2. And we're going to hear a talk later today, a speed talk by Avery Tatters. He's going to talk about the story with Alexandrum cananella from the West Coast and how that's affected by high levels of CO2. And then the final point I'm going to make has to do with the co-occurrence of harmful algal blooms and high levels of CO2 and how that might be affecting fisheries and other marine resources. And again, for this, I'm going to rely on data from New York, in this case looking at Oreococcus, the brown tide. And in order to address the effects on marine resources, we first again wanted to map out the levels of CO2. And that's what's shown here. And it's actually a strikingly similar pattern to what we saw with Alexandrum. So we're looking at the South Shore of Long Island now. This is the Shinnecock Inlet to Shinnecock Bay, exchanged with the Atlantic Ocean. You can see the transect that was made is from the inlet going to the back part of the estuary. And as we do so, we see the levels of CO2 transitioning to what we call a normal level to levels that are quite high in the back part of the estuary. Concurrently, we're looking at densities of Oreococcus, and what we found is that, again, in the back part of the estuary, we're seeing not only high levels of CO2, but very high levels of Oreococcus in this case, over 2 million cells per milliliter. And a tight correspondence between the high levels of CO2 and the higher densities of Oreococcus. Now, we concurrently measured pH at the same time, and that's what's shown here. So here's a surface transect continuous monitoring of pH with a CFET sensor. And as we expected, not only high level of CO2, but low pH during the brown tide bloom in June. But what was interesting and surprising is that later in the season, we didn't see this pattern. So once the brown tide went away, it started in May, it continued into June, but it was gone by July. The rest of the season, we did not see the extremes that we saw during the Oreococcus bloom. And that's despite the fact, as I showed you before, the data set from Keel Bay, that in most estuaries, the peak in CO2 levels occur in the late summer. And so it was slightly acidified, but not to the extent we would have expected. And so suggesting that this acidification was unique to Oreococcus. So if we accept this as that normal algal blooms may increase the high level of CO2, there may be some special cases when it comes to halves, and also some feedback that exists as well. So that is to say, if you consider dense blooms such as Oreococcus, those very low levels of light and high turbidity are going to turn the system into being net heterotrophic, so more likely to produce high levels of CO2. Moreover, Oreococcus and actually a lot of other halves are heterotrophic in their metabolism, so that is, they may be using organic compounds and therefore producing and not consuming CO2, and this could create some positive feedback. Now, to get to the question of how the halves are affecting, when they're co-occurring with the CO2, how that's affecting fisheries, to answer that final question, we look specifically at bivalve larvae, and specifically bay scallops, which we know are impacted by both of these factors. And that's what's shown here, exposing bay scallop larvae to both different levels of CO2 and also a diet of Oreococcus compared to a controlled diet of Isochrysis. And we do see a CO2 effect on these larvae. They're calcifying larvae, and therefore high levels of CO2 interferes with their ability to calcify. And so that's sort of the ocean acidification effect that a lot of people have looked at, for example, Pacific oysters. We also see that Oreococcus knocks down their survival significantly, and when they're exposed to both stressors, there's actually a synergistic effect. That is to say, statistically, this is lower survival than would have been predicted from either individual stressor. Now, we also look at this in an ecosystem setting. See, I'm running out of time, so I'll speed it up. And that is to look at the settlement of bivalve larvae across the system where we know there is acidification. That's shown here. We're looking at 4 different species of calcifying bivalves. We're collecting these larvae as they settle over the summer season through the occurrence of a brown tide and the occurrence of high CO2. And you can see there's lots of stations, but essentially the bay breaks in half to the point where there's an area where they're settling and an area where they're not settling. And if you look within the estuary, we see high rates of settlement in this area where there's no brown tide and there's no acidification. Conversely, in this back part of the estuary where we're getting brown tides, we're getting acidification, we're not seeing these calcifying larvae settle. And it's not just the calcifying larvae, but even shellfish larvae, fish larvae, larval fish, are also sensitive to high levels of CO2. So we need to be thinking beyond just the calcifying organisms. And so, in addition to this model we had previously, we can add in the co-effects of both halves and high CO2, potentially affecting fisheries. And this may even be the case, there's no effect of CO2 on the halve that you're studying. And there are species out there that won't be affected by CO2.